We now turn our attention to internal forces. In our previous analyses, we've been focused on the loads communicated between rigid bodies. Our free body diagrams have isolated single members or assemblies of members, but we haven't isolated a fraction of a rigid body. We now propose to do just that, cutting through a member and looking at forces and moments that develop inside it. More importantly, we're not just interested in the internal forces that develop at a single discrete location. Instead, our interest will be in developing expressions for internal loads as a continuous function of position as we move from one side of the member to the other. Having such information is crucial when we make the transition from rigid to deformable bodies. Internal loads as a continuous function of position are one important input to understanding how members deform under load. Our focus will be primarily on what we're going to call slender members. These are structural elements whose lateral dimensions are small compared to their length. These members are used extensively in construction and fabrication, and so are of great interest to those in the civil and mechanical engineering professions. We'll begin by examining internal loads at discrete locations in members. We'll then focus exclusively on straight beams to develop expressions for internal loads as continuous functions of position. We'll look at two approaches for this, an equilibrium approach and an integration approach. You can think of these two approaches in much the same way as you might think about method of joints and method of sections in truss problems. Both approaches provide the same information, but there are instances when one approach is more advantageous than the other. You should work to develop comparable fluency with both approaches. For now, we'll begin with some nomenclature and a focus on finding internal loads at a few discrete locations. Internal loads are forces and moments that develop within a structural member due to the external loads applied to it. As just mentioned, our focus is going to be on slender members, but this raises the question, just how small do the lateral dimensions have to be in order for a member to be classified as slender? This collapsed bridge column appears to have a lateral dimension comparable to the height of the man standing next to it. How could this be slender? A good rule of thumb is that a member can be considered slender if its lateral dimensions are 1/10 or smaller of its length. This particular column failed during the 1989 Loma Prieta earthquake in the San Francisco Bay Area. It would be difficult to use our previous expression for critical buckling load to understand the basis for the failure. First, this is a composite structure. It's steel-reinforced concrete, so it isn't a homogeneous body. Second, the dynamic loading experienced during an earthquake, in particular the component responsible for side-to-side swaying, renders our static critical buckling load expression quite simplistic. Slender structural members appear in many different disciplines. For those interested in mechanical engineering, the bicycle frame is a welded assembly of slender members. For those interested in biomedical engineering, human bones can be modeled as slender members, although most of the elements, including this femur, are complicated composite objects. For those interested in civil engineering, the columns and cross-sections of this pier can be treated as slender members. As you look at these pictures, think about the ratio of lateral dimension to length for each member. The 1:10 ratio appears to be well represented by these examples. In contrast, this casting has some delicate features, but the overall geometry is short and squat. There is no clearly defined small lateral dimension. This slide introduces the nomenclature we'll use for internal forces in slender members in 2D. The first question that arises is this: what set of loads do we expect at a cut through a rigid body? We can go back to our rationale for including reactions for different supports on bodies. We have a reaction component for every degree of freedom that is prevented or impeded. In the case of a 2D rigid body, one side of the body is not permitted to experience arbitrary displacements or rotations relative to the other side, so we have two forces and a moment at the cut plane. In this case, we're not permitted for one side of the body to open up an axial gap That would represent a discontinuity in the axial displacement, and this gives rise to our axial force N. We're also not permitted to have a discontinuity in vertical displacement, and this gives rise to a shear force V. And we're not permitted to have a kink in the body where one side has a completely different orientation with respect to another. That would represent a discontinuity in rotation, and so we end up with a bending moment M. Likewise, in 3D, we have 3 forces and 3 moments at the cut plane. There is no difference in the number and character of loads at an internal cut than there is at a built-in support on a full rigid body. In one case, the built-in support, the degrees of freedom prevented or impeded are absolute. In the other case, the internal cut, the degrees of freedom prevented or impeded are relative. In both cases, we have a full complement of loads. For 2D slender members, it's important to note that our cut through the member will be perpendicular to the long axis of the member. The axial force, or normal force N, is normal to the cut plane, directed along the long axis of the member. The shear force V is parallel to the cut plane and perpendicular to the long axis of the member. The bending moment M is in the out-of-plane direction. Note the exaggerated deformations accompanying each load shown along the bottom of this slide. The axial force N is the same load that is carried by our straight truss members. It stretches the member if it's in tension and squashes the member if it's in compression. Truss members tend to be very stiff along their long axis, so it's often difficult to see the deformation associated with this load. Although we'll solve for N a few times, our primary interest will be on V and M. Both of these loads contribute to deformation lateral to the long axis. The shear force V causes lateral distortion. Note that an unloaded rectangular coupon of material has developed into a rhomboid shape on loading, as shown at bottom center at B. The moment M causes the material to flex, as is shown in the bottom right at C, and is called a bending moment. The sagging or bending of beams and other slender members is of great interest in structural engineering and will lead us to focus on V and M. Another important topic related to these internal forces has to do with sign convention. What shall we designate as a positive internal load? For now, we'll focus on the axial force, as that is the most intuitive of the three. We think about tension as positive, something that stretches or lengthens a member, and compression as negative, something that squashes or shortens a member. We will take N as positive in tension. The equal and opposite internal forces shown in the middle of the slide both represent tensile or positive N. This is sometimes a source of confusion. We note first that if we're isolating a fraction of a member, there will be a cut plane that faces in one of two directions. The cut plane on the left has an axial force N that points in the plus x direction. The cut plane on the right has an axial force N that points in the minus x direction, yet we designate both of these as positive. A physical interpretation is that both forces are tending to lengthen the member, are tensile, and hence are positive. Another interpretation combines the forces with the cut planes on which they reside. We assign an outward unit normal to each cut plane and designate it as a positive or negative face depending on how the outward normal is oriented. The cut plane on the left has an outward unit normal that points in the plus I direction. Hence, the cut plane is a positive face. The cut plane on the right has an outward unit normal that points in the minus I direction. Hence, the cut plane is a negative face. A force in a positive direction on a positive face is positive. But a force in a negative direction on a negative face is also positive. As is designated in this slide, we can think about this in the same way that we would multiplying two scalar numbers together. The product of two negative numbers yields a positive value. In 3D, the full complement of internal loads gives us 3 forces and 3 moments at the cut plane. The axial force N plays the same role in 3D that it does in 2D. The internal loads Vy and Mz tend to be grouped together as both promote bending in the xy plane. The internal loads Vz and My tend to be grouped together as both promote bending in the xz plane. The axial moment Mx is called a torque or twisting moment because it produces a very different kind of deformation than the bending moments My and Mz. As with N, we'll rarely be focused on the axial load Mx, but we may run into it occasionally. Although no sign conventions are listed on the slide, all the loads shown here would typically be designated as positive. The left cut plane is facing in the plus I direction, and all the loads in the left cut plane are shown acting in the positive coordinate directions. Loads on positive faces in positive directions are positive. The right cut plane is facing in the minus I direction, and all the loads on the right cut plane are pointing in the negative coordinate directions. Loads on negative faces in negative directions are also positive. You might note, in comparing slides 6 and 7, everything is consistent except for the direction of V in the 2D slender member. We'll come back to that shortly. Our approach for establishing equilibrium is no different from what we've done previously with whole rigid bodies. We now have to choose an isolating surface that passes through the rigid body, draw the appropriate free body diagram, and, if possible, solve for the unknown internal forces. We'll take a look at how to do this with 3 example problems. In our first problem, we have a C-clamp used to press 2 pieces of wood together. If the clamping force is 200 newtons, we want to determine the internal forces acting on cross-sections through points A, B, and C. We have a purely axial 200 Newton load applied along this threaded member. We're going to take as our free body diagrams these isolating surfaces, A, B, and C. For A, we need not be too concerned with representing the clamp geometrically. We're going to have a 200 Newton force here applied at the top of the workpiece, and through the cut at A we'll have a normal force at A, a shear force, and a bending moment. Our equilibrium expressions will be very simple. We have VA equals 0 from force equilibrium in the x direction. Force equilibrium in the y direction will give us NA minus 200 newtons equals 0, or NA is 200 newtons. And sum of the moments about A equals 0 gives us the bending moment at A plus a positive moment due to the 200 Newton force, which acts through a moment arm of 50 millimeters as shown on the figure at left. So we have the bending moment at A is minus 10,000 Newton millimeters, or minus 10 Newton meters. For the free body diagram at B, we again have our 200 Newton load, and now normal force at B, shear force at B, bending moment at B. Equilibrium here gives us NB is equal to 0 in the x direction. In the y direction, we have VB minus 200 newtons is 0, or VB is equal to 200 newtons. And sum of the moments about B equals 0 gives us MB plus the positive moment exerted by the 200 Newton force, now through a distance of 30 millimeters, and this gives us MB is minus 6,000 Newton millimeters, or minus 6 Newton meters. Finally, at C, we have a relatively simple situation. We have the threaded member subjected to a 200 Newton force from below, and our normal shear and bending moments at C will look like this. And we can see from this free body diagram we're going to get a very simple result. Force equilibrium in the x direction is going to give us that the shear force C is 0. Moment equilibrium about C is going to give us that MC is 0 Newton meter. And finally, axial equilibrium is going to give us that the normal force at C is minus 200 Newton.